Alright, it has been a very long time since I've uploaded a video. Been spending a lot of time focusing on research, but now with this being like end of April 2020 and a lot of quarantine going on, I have a little extra time, so I figured I would get back into these videos. So, I got this problem, and so what we have is we have these two functions which are integrable. And we want to show that that implies that their product is also integrable. This is actually a little interesting because I was looking into this a little bit, and basically we're able. Well, the fact that this problem comes at the beginning of the section implies that it should be an easy problem, or at least a quicker problem, and it turns out to be so. And the reason that is because we basically we get to use facts about sets of measure zero. Whereas if you look in a textbook like Principles of Mathematical Analysis by Walter Rudin, also known as Baby Rudin, the textbook is also known as that. If you look at that, then what you see is a slightly more complicated proof where you have to basically what you have to do is you have to do this really weird unintuitive thing where you use the fact that if you pass an integrable function through a continuous function, the resulting function is still integrable. It's something like that, I think. But anyways, you use that, and then you show that if you have a function f which is integrable, then the function f squared is integrable. And then you write f, you use something like, 4 times fg equals quantity f plus g squared plus quantity f minus g squared, right? No, you'd have to subtract quantity f. Well, let's think about it, because f plus g quantity squared, that'd give you f squared plus 2fg plus g squared. And so you want to cancel out the f. Yeah, so you would subtract the quantity f minus g squared. And so you'd have what you'd end up is you'd be subtracting f squared, subtracting g squared, so the f squared and g squared terms cancel. Then you get the 2fg minus negative 2fg, so you get 4fg. And so basically what you have is 4 times fg is equal to a sum of two functions which are squares of sums of integrable functions. And so you use the fact that sums of integrable functions are integrable, and squaring an integrable function gives you an integrable function to prove that the product f times g is integrable. So that's a little complicated because you have to prove this separate theorem that passing f through a function gives you an integrable function. But here, all we have to do, which I probably, if I had started writing it down, I probably would have been done, is we just use sets of measure zero. And so this also goes to show sort of the usefulness of sets of measure zero and measure theory in general, is that allows you to simplify things. Anyways, okay, so f and g are integrable. I looked in the textbook. I'm not sure if this has been brought up explicitly, so I want to emphasize it. And maybe it's just straightforward enough to have not been mentioned, but let's just mention bounded functions are not. Yeah, maybe this is just me being rusty on my definition. So at this point, our definition of integrable does not include unbounded functions. Of course, there are unbounded functions which you can define an integral of, but we're not there yet. Right now, our definition of integrable functions requires those upper sums and lower sums, and the difference being able to be made arbitrarily small by choosing an arbitrarily fine partition. But given this definition, bounded functions are not integrable. What am I talking about? Unbounded functions. unbounded functions are not integrable. Because if f is unbounded, then the upper sum of f given any partition P is always going to be infinity. Because there's always going to be... so if it's unbounded, that means there's like a place where it's tending to infinity or possibly minus infinity. Let's just look at the basically you're going to have a region. I'm not even going to write it. I'm just going to state it. You're going to have a region where you're going to positive infinity or negative infinity. And so you've got some set in your partition which includes those points that are getting closer and closer and closer. And so if you take the infimum of the function or the supremum, depending on whether it's going to upper or positive infinity or negative infinity, you're going to get either positive infinity or negative infinity. And so it's not going to be possible to bound the upper sum. Well, if either the upper sum or the lower sum is not a finite number, then it can't be integrable. So unbounded functions are not integrable. So f and g are integrable. So despite me rambling a lot, I do like when you can simplify things. So here, instead of writing out integrable, I'll just do an integral sign and then bool. So integrable. Okay. So f and g are... this isn't even what I meant to say. So f and g are bounded. Okay. Well, obviously we knew f and g were integrable. We're told that. Okay. Unbounded functions are not integrable, so f and g are bounded. So let Bf be the set of discontinuities of f. So Bf consists of all points x such that f is not continuous at x. And we call it Bf because we want to be able to refer to Bf and Bg separately. And in the textbook, there was a theorem where they referred to the set of discontinuities of a function f as b. So we'll just use that same lettering here, and we'll call it Bf. Anyways, so theorem 3-8 says that the measure of Bf and the measure of Bg are 0. Now, of course, in this textbook, they haven't brought up, typically when you talk about measure theory, this mu is a function, and it is defined as your measure, and you feed in a set, and you get the output of the function is the measure of the set. So it's a notation that I like to use. Of course, in the textbook, they haven't talked about that, I don't think. Oh, maybe they have. Maybe they've used lowercase m for measure. But in any case, I'm going to use this. You can write it however you want. Maybe you can just write out the words Bf is a set of measure 0. Okay, but anyways, theorem 3.3-8 says that basically a function is integrable if and only if, it has to be bounded, I believe. A bounded function is integrable if and only if it has measure 0. So if you've got a bounded function, a bounded function is integrable if and only if its set of discontinuities has measure 0. Okay, so f and g are functions which are integrable, and so their sets of discontinuities must have measure 0. So the measure of Bf union Bg also equals 0, and that was a theorem from, I think, the previous section where you can take countable unions of sets of measure 0 and still have a set of measure 0. Okay. BFG. So this is the, so B, B, and then the subscript is F times G. So I'll write this. So this function in the subscript is F times G. So this is the set of the set of discontinuities of the function F times G. And this set is a subset of BF union BG, because if F times G is discontinuous at a point, then it has to be discontinuous at least F or G. I mean, it's possible that you can have a point in BF or in BG, which is not in BFG. But if you've got a point of discontinuity of F times G, then it can't be the case that both F and G are continuous at that point. For F times G to be discontinuous at a point, either F or G needs to be discontinuous there, or or is inclusive or, so possibly both. Okay. And so this is a subset of a set of measure 0, and so that means that it has measure 0. So measure of F times G equals 0. Okay. So F and G, again, we need a bounded function. For bounded functions, integrability is equivalent to set of discontinuities having measure 0. So F and G are bounded. So F times G is as well, because you could just take the bounds for F and the bounds for G and multiply them together, and those give you the bounds for F, the function F times G. Okay. So by 3-8 again, F times G is integrable, and that's what we wanted to prove. So basically what this is using is it's using facts about sets of measure 0, and we're also using theorem 3-8 in both directions. And that's about all there is to the problem. Again, I went into a lot more detail about some of the more interesting aspects, I guess you could say, although this is more of a simple problem, so how interesting you find it, I mean, that's up to you, but still there is some things to be said about other ways of going about proving this, but I talked about this at the beginning of the video already. But yeah, so that's about all there is to this exercise, and so we are done.